All right, welcome everybody. Today we're going to talk about lesson number 55. This is still section 5.1 using trig identities, and we'll just call this day 2. Now, while we are going to see some of those same algebraic simplification techniques that we did in the previous lesson, we're going to focus more on some specific strategies that we're going to need for calculus. The truth is we probably didn't need to do this lesson using the flipped classroom, but in order to keep the progression and the schedule, we're just going to go ahead and keep it this way. So here in number 1, you're going to go ahead and try to use trig identities to find all 6 trig functions given those 2 pieces of information. So notice I started by writing the 6 trig functions. The variable in question is u. I wrote the big 3 on the left side and then their reciprocals on the right side. In the past, you most likely would have solved this problem by drawing a triangle and using SOHCAHTOA. Technically, that still works. But because chapter 5 is really all about the formulas and the identities, we're going to try to solve it that way to make sure that we get the practice. No matter how we're solving it, we do still care what quadrant is this all taking place in. So remember, each piece of information eliminates half of the possibilities. So the fact that the secant is equal to a negative, secants are only negative in quadrants 2 or 3, which is why we're allowed to eliminate the right-hand side. Then further, if the tangent has to be positive, tangents are positive in quadrant 3, which is how we know that this is a quadrant 3 situation. So we do want to keep that in mind in terms of the positivity and the negativity. So if we want to solve this problem, but preferably without a triangle and using an identity, let's go ahead and first write in the given information, which is the fact that the secant is equal to negative 3 over 2. And then the easiest identity to use for that is the fact that the cosine of u is equal to 1 over the secant. And again, if you can't remember that, you can simply go back to your formula sheet and you can see here that the cosine is equal to 1 over secant. And remember, it works for any variable. So the cosine of u is going to be equal to 1 over negative 3 over 2. And if you multiply by the reciprocal, you're going to go ahead and safely be able to say that the cosine of u is equal to negative 2/3. And yes, it's possible you don't even have to do any work to find that answer, but I'm just trying to show you that the focus here is supposed to be on using the identities. So now, again, trying not to draw a triangle, I need to solve for one of these other 4. There's a couple of different ways that you could do it. I'm actually going to try to find the sine next. So if I'm going to try to find the sine next, I need to find some identity that connects the sine to a different trig function. And I'm going to use the one that I think is the most popular, the fact that sine squared plus cosine squared is equal to 1. So a little bit of room here. I'm going to go ahead and do it off to the side. So the sine squared of u plus the cosine squared of u is equal to 1. That is always true, no matter what the variable is. So the sine squared of u is equal or is added to the cosine, which we found was negative 2 over 3 squared is equal to 1. So sine squared of u is equal or added to square the top, you get 4. Square the bottom, you get 9. And then instead of saying 1, I'm going to convert that to be 9/9. So the sine squared of u is equal to 5/9. And now you're going to go ahead and solve for the sine of u. How do you get rid of a squared? You take a square root. When you take a square root, it's plus or minus, and you can break it up into the square root of 5 over the square root of 9, which would just be 3. Then you have to decide, is it the positive or the negative? And how do you know that? Well, it all depends on what quadrant you were in. So we decided earlier that we were in quadrant 3. Sines are negative in quadrant 3, so that's the one that we're going to choose. So going back to our list here, the sine of u is going to be equal to negative the square root of 5 over 3. Then once we have that, the fact that the cosecant is equal to 1 over the sine of u, that means that you can do 1 over the square root of 5 over 3, or you can simply just flip it. So that would be negative 3 over the square root of 5, which would become negative 3 radical 5 over 5. So we've got the sine and the cosine and the cosecant and the secant. And now finally, when it comes to finding the tangent and the cotangent, well, of course, we remember that the tangent is equal to the sine of u over the cosine of u. And if you were to forget that, go back to your handy reference sheet here. That's one of the quotient identities, so sine over cosine. That's going to go ahead and give you the square root of -5 over 3, that negative, over -2/3. Because of the fact that they have the same denominator, the 3's would cancel, the negatives would cancel, and you would get positive square root of 5 over 2. Then the cotangent is equal to, you could say, the cosine of u over the sine of u. And again, you could get that from your formula sheet if you need to. So again, the 3's would cancel, the negatives would cancel. That would give you 2 over radical 5, which would, of course, be 2 radical 5 over 5. So your mission was to find all 6 trig functions, which you've done here. And because of the fact that you're in quadrant 3, remember that the only things that should be positive are the tangent and the cotangent. So it looks like that tracks. Now you might be thinking, well, okay, what if instead of finding the cotangent as cosine over sine, what if I wanted to do 1 over tangent? Well, yeah, that would work too. And again, am I going to be able to come to your house and force you on a test to do it this way as opposed to drawing a triangle? Yeah, probably not. But again, you're only going to see a handful of these. So my advice, try to use the actual identities, really, because that's the point here of chapter 5. A little bit more direct here in number 2. So they're telling you to make a substitution. They're telling you to take the x and let it be equal to 2 times the tangent of theta. They're giving you a qualifier here that theta has to be between 0 and pi over 2. And they're asking you to rewrite the square root of 4 plus x squared as a trig function of theta. So if you take a look at this restriction on theta, the fact that it's between 0 and pi over 2, that means that it's a quadrant 1 situation. And the truth is, we love when things are quadrant 1 because we don't really even have to think about them. Everything is positive, everything is defined, we're not going to come across any issues, so life is good. The square root of 4 plus x squared, please do not pretend like you know what that is equal to. It is not 2 plus x, it is not 2 minus x, it is not something that you know. So we're going to go ahead and actually make the substitution. Everywhere there's an x, we're going to put a 2 tangent of theta. So the square root of 4 plus x squared is now going to become the square root of 4 plus 2 tangent theta, the whole thing squared. Oh, well, lost my theta. Hang on. Okay, so now when you go ahead and square, you're going to get 4 plus, square the 2, you get a 4. Square the tangent, you get a tangent squared, and make sure you put the squared in the right location between the tangent and the theta. That's looking good. We like that, but there's more to be done. There's more to simplify. So 4 plus 4 tangent squared. I do know the square root of 4, but I can't do anything about it right now, not until I factor it out. At first, I'm not going to factor it out of the radical. I'm just going to factor it out of each of the terms. Now that I've done that, something else that I realize, 1 plus the tangent squared. Again, the 1, the squared, that is kind of calling out to me that it might be an identity. So if I go back to my formula sheet, 1 plus tangent squared looks like that is equal to secant squared. So I'm going to go ahead and further make that substitution. So this is now going to become the square root of 4 times the secant squared of theta. And then life is really excellent because the square root of 4, that's a 2. The square root of the secant squared, that's just a secant, which means the whole point of this problem was I wanted to get down to 2 secant of theta. Sooner rather than later, there's going to be more that I want to do with that. But for now, you're just making sure that you can do the substitution. And again, when you're talking about the square root and things you're allowed to take the square root of, it's all because of the fact that we had this quadrant 1 qualifier here, which means no plus or minus, no negatives, no undefined. Life is good, and it's business as usual. We're going to see a very similar scenario here in number 3. So if you're watching this video at home, feel free to pause and try it if you want to give it a shot. Otherwise, again, we have this value of x. We're being asked to make a substitution into this expression. And again, we're given that important quadrant 1 qualifier just to let us know that there isn't going to be any crazy stuff to watch out for. So we're going to go ahead and again make that substitution. So we're going to get the square root of 25 minus x squared. That is going to be equal to the square root of 25 minus 5 sine of theta, that whole thing squared. That becomes the square root of 25 minus, square the 5, you get a 25, square the sine, and you get a sine squared. Make sure you're putting it in the proper location. Square root of 25, that seems like something I know, but I first want to factor it out. I don't want to factor it out yet of the radical. I just want to factor it out of each term. Then again, 1 minus sine squared, well, that kind of reminds me of one of those identities. So back to my formula sheet, that has something to do with this first one. If I was to rewrite this as 1 minus sine squared, that would simply leave me with a cosine squared. So I'm going to go ahead and be able to replace that 1 minus sine squared theta. I can go ahead and replace that with a cosine squared theta. And then again, from here, life is good. The square root of 25 is 5. The square root of the cosine squared is the cosine, which means I wanted to do all that lovely work to get me down to 5 times the cosine of theta. Again, in just a second, you're going to see what the next step is. But for now, everything is in quadrant 1. So everybody's happy, everybody's positive, nothing is undefined, and life is good. If you're wondering, is it always going to be a perfect square? Is it always going to be a squared? Most of the time, yes. Not that you couldn't do it. If it isn't, it just gives you a messier answer. And for now, we're really focused on those nicer problems. Okay, so what is an extension of that? Well, an extension of that would be something like number 4. Notice now that they're still telling you to make a substitution, but you're substituting it into an equation as opposed to just substituting it into an expression. So that is a slightly different story. I'm substituting x equals 6 times the sine of theta. And then notice we have a little bit of a different qualifier here. They're telling you now that theta is between negative pi over 2 and pi over 2. So hopefully you can recall that that means we're talking about quadrant 4 or we're talking about quadrant 1. So something that we really want to consider as we move through the problem. And then don't forget this little bonus question here. They're asking you for the sine of theta and the cosine of theta. So every piece of information that's given to you is important. Make sure that you make the substitution, do all the algebra that you can, and then in the end, don't forget to actually find the sine and the cosine, and of course, keeping in mind what quadrants the problem is taking place in. So the first thing we're going to do is we're going to go ahead and we're going to make that substitution just like the previous problems. Everywhere there's an x, I'm going to go ahead and put the 6 sine theta. So again, we have an equation now. So 3 is equal to the square root of 36 minus the quantity 6 sine of theta, the whole thing squared. Then from here, we're going to go ahead and under the radical, we're going to get 36 minus 36 sine squared of theta. So 3 is equal to the square root of 36 factored out is 1 minus sine squared theta. And then just like the previous problem, 1 minus sine squared theta, that's going to be equal to cosine squared theta. So 3 is going to be equal to the square root of 36 cosine squared theta. And again, the reason why I'm allowed to make that substitution is because of the Pythagorean identities. Then finally, the good news is that the square root is going to be gone in the next step. I'm going to be able to say that 3 is equal to the square root of 36 is 6 cosine of theta. So from here, I am then going to go ahead and solve for the cosine of theta. That was one of the things that I wanted to do. So now that I've gotten down to this point, I'm going to go ahead and solve for the cosine of theta by dividing both sides by 6, which I can then conclude that the cosine of theta is equal to positive 1/2. So the cosine of theta is equal to positive 1/2. And if you check that against these qualifiers about the quadrant, that should make sense. Cosines are x values. X values are positive in quadrants 1 and 4. So good news, everything matches up. But now I have to go ahead and find the sine of theta. And again, there's a couple of different ways that I can do that. I'm going to do that using an identity. using, again, what's usually the most popular one, the sine squared of theta plus the cosine squared of theta is equal to 1. So that's going to tell me that the sine squared of theta is added to 1/2 squared is going to give me a fourth. And then instead of 1, I'm going to say 4/4. That's going to tell me that the sine squared of theta is equal to 3/4, which means to get rid of the squared, I'm going to take the square root. When I take the square root, I'm going to, of course, do my plus or minus. The square root of the top is the square root of 3. The square root of the bottom is just 2. And then it becomes a matter of, are both of those my answers or not? Well, the fact that this problem is either quadrant 1 or quadrant 4, signs are y values. So if you're in quadrant 1, the sign should be positive. If you're in quadrant 4, the sign should be negative. So it actually is both. So the cosine of theta is equal to positive 1/2, but the sine of theta is equal to plus or minus the square root of 3/2. Again, the pluses and the minuses depend on the quadrant, but those values of 1/2 and root 3/2, those should look familiar because those are, of course, from the unit circle. All right, so now let's take a look at number 5. Rewrite the ln of the absolute value of the cosecant of theta plus the ln of the absolute value of the tangent of theta as a single log and then simplify the results. Ooh, the natural log. Logarithms back to town. Ooh, you're welcome. That's exciting. Even though the problem might seem more difficult, although I promise it's really not, the one good thing you certainly have noticed about today is that the problems certainly give you a lot more information about what it is you're supposed to do, as opposed to the problems yesterday, where they mostly just said simplify, which means there's a lot of different ways that could go. So if nothing else, at least be grateful that there is more directions. Just a note here about these absolute value bars. Hopefully you remember that natural logs or logarithms in general, a natural log of course means base e, but you're only allowed to take the log of something that is positive. So no logs of 0 and no logs of negative. So they have those absolute values there just to kind of drive home the point that you're only allowed to take the logs of positives. So if they are in your problem, you need to keep them down to the end. So we're going to go ahead and try to rewrite this as a single logarithm. First, we're going to go ahead and focus on the trig part of it. So the trig part of it is we're going to look at the cosecant and we're going to look at the tangent. We're going to rewrite those as some other combination of trig functions. So we're going to keep the natural log, we're going to keep the absolute value, but we're going to rewrite the cosecant as 1 over sine of theta. Then plus, we're going to keep the natural log, we're going to keep the absolute value, but we're going to rewrite a tangent as a sine of theta over a cosine of theta. And again, if you're having trouble remembering why those pink expressions turn out to be 1 over sine and sine over cos, all you have to do is go back to your formula sheet, and that's going to go ahead and help you every single time. Now you'll notice that we have to use some properties of the logs. So we have logs of the same base, e, being added. Think back to your log rules. What are you supposed to do or what are you allowed to do if you have logs of the same base being added? Well, this is the product rule, which says you're allowed to multiply them. So my next step is I'm now going to have the natural log inside the absolute value. I'm going to go ahead and multiply 1 over sine of theta times the sine of theta over the cosine of theta. That is the product rule back from the log chapter. Now a little bit of algebra. I'm going to go ahead and be able to reduce those signs, which means I can now conclude that this is equal to the natural log of the absolute value of 1 over the cosine of theta. And then while that is a pretty good answer, I do notice that 1 over the cosine of theta, that can be written in a slightly simpler way if I go ahead and change that 1 over cosine into a secant. And it turns out that that is what I'm looking for. I am looking to take, again, that big, messy expression and turn it into the natural log of the absolute value of the secant of theta. Now, there's lots of things, again, additionally, that I could do with this, but for now, you're just trying to practice the mechanics. A little bit something similar here in number 6, you again have some log expressions that you are being asked to combine. Something you want to notice here, we don't have absolute values, and let's talk about why. Notice that inside of the first ln is a cosine squared, By definition, a squared quantity is always positive, so no absolute value bars required. And it's the same reason for the second one. The tangent squared will always be positive, and then if you add 1 to it, certainly it's going to remain positive. So the first thing we're going to do is we're going to focus on the trig part of it. So we're going to take the cosine squared of theta, and the truth is the cosine squared of theta seems pretty simple to me. So I'm going to go ahead and leave that as the ln of the cosine squared of x. And I guess they're x's instead of thetas, but again, the variables are interchangeable. So then 1 plus tangent squared. If you look at 1 plus tangent squared, that kind of looks familiar. And if you can't remember, go back to your formula sheet. 1 plus tangent squared, here it is. That is equal to a secant squared. So you're going to go ahead now and make that replacement. So plus the ln of, instead of 1 plus tangent squared, you're allowed to write that as the secant squared. Then from there, perhaps you realize that you can do a little bit more rewriting. You have the ln of the cosine squared plus the ln. So a secant is a 1 over a cosine. So a secant squared is a 1 over a cosine squared. And again, formula sheet if you need a reminder. Then, because you have logs of the same base being added together, this is yet another product rule situation, which says that you are going to have the ln of the cosine of squared, cosine squared of x times 1 over the cosine squared of x. Would you look at that? You can go ahead and cancel out those cosines, which means you're going to get the ln of 1. And hopefully, if you remember, because this is base e, the ln base e of 1 is really asking yourself e to the what power equals 1, which means this whole problem just turns out to be 0. And God, I want to live in a world all the time where that big, messy, ugly problem turns out to just be 0. Oh, that is the dream. So just to circle back to day 1, our final problem here is a little bit more of the type of what you saw yesterday in lesson 54. Rewrite the expression so that there's no fraction. So they're not giving you a ton of information. And so you kind of have to decide what it is that you're going to do. I'm going to go ahead and give you a little clue. In this case, you're going to look at the denominator, 5 over tan x plus secant of x. If you go back to your formula sheet, you will notice that, again, there is an identity that connects a tangent and a secant, but they have to be squared. There are no squares currently in the problem, and that's an issue because they have to be squared for it to work. So how do you take a problem that doesn't have any squares and how do you make some? Well, you're going to multiply by the conjugate. We've talked about conjugates a few times now. Remember that a conjugate is the same front, the same back, and the opposite middle. So obviously 5 doesn't have a conjugate, so I'm going to take the conjugate of the bottom, which would be the tangent of x minus the secant of x, and then 1 on the top and 1 on the bottom, because that's the only way that it works. So on the top, you have to distribute 5 times the tangent of x minus 5 times the secant of x. And then remember the rules for multiplying denominators. If they are going to be conjugates and the difference of squares, then definitely multiply away. So that's going to give me a tan squared minus a secant squared. Remember, all you need is first and last. The whole goal here was to get some squared action, which we do have. So let's go back and confirm what the heck is that equal to. I go back to my formula sheet. If I take my tangent squared and I subtract the secant squared over to the left, I'm going to have to move the 1 to the other side, which is going to be equal to a -1. So a tangent squared minus a secant squared is equal to a -1, which means I'm going to go ahead and be able to sub that in. So 5 tangent of x minus 5 secant of x, and that's going to be divided by -1. Instead of having that messy -1 in the denominator, I'm going to go ahead and divide through by the -1. So if I divide through by the -1, that's going to turn this into a minus and this into a plus. And in my final answer, I'm going to factor out the 5. Then I'm going to put the secant of x first, and then minus the tangent of x second. And that is, in fact, what I'm looking for, mostly because of the fact that it got rid of the fraction, which is exactly what the problem asked me to do. So homework 55, you're going to go ahead and see underneath here. Remember that we are going to do this the next time class meets during class so that you can ask questions and work together. And hopefully that'll lead to a better and deeper understanding. So thanks very much, guys, for tuning in, and we will catch you next time.